Okay. Okay, so first, before I start on the midterm review, any questions? Have you guys put in your proposals?
No.
Okay, okay.
Should it be one per team or everyone should submit it?
One per team.
Yeah, okay.
And I made it as a group submission on Gradebook, but I've never used that capability. So tell me if it shows up as a group assignment or something. I don't have a student account, so I can't see how it looks, but they seem to have some notion of a group assignment. So in any case, hopefully it will ask who your partners are, and but you just have to submit one. Okay. I also posted a little write-up on Bluetooth. I'm going to go over that in tomorrow's lecture, which will be just a standard lecture. So this one, what I wanted to do was I'm going to post these slides. First, I want to go through the concepts, key concepts we have covered thus far, and also go through some sample questions. Okay. And just stylistically, so it's just 50 minutes exam, right? So we can't really yeah, sort of uh, go into anything very elaborate. So basically have a combination of true false questions, multiple choice, and short answer, primarily to see that you can uh, reason, firstly, that some of the concepts that are you familiar with them, and the other thing is, can you reason about them in very simple settings, perhaps some simple numerical settings. The only part of the material we have covered which is conducive to problem solving is the part related to scheduling and some of the parts related to energy and duty cycling. So those are the parts where you can expect some numeric problems. Rest of the stuff would be more conceptual in nature. So what I wanted to do was to go over kind of a quick brush through the main concepts we have covered, just so that you remember them, and also recall that we allow for one cheat sheet, two-sided, 8.5 by 11. The idea behind the cheat sheet is so that you are forced to go through the material. Okay, so don't defeat that purpose. I guess that's what I'm trying to say. Okay, so we started this course by kind of looking through some of the characteristics of the embedded platforms, and this was kind of the generic picture. But one of the very first thing we had covered was different choices that exist when it comes to selecting the technologies. In particular, on one end, you have microprocessors, and then kind of increasingly more specialized things. So processors, which are domain specific, microcontrollers being the one which we used quite a bit. Just by way of recalling your memory, so what is a microcontroller? Like, how does it differ from a microprocessor? So it and memory and peripherals. So basically, it's kind of like a whole computer trying to put onto a single chip. Um, and then there are others that are encountered, but at least that's not what we have on the platform we are using, but application-specific processors, and going all the way to ASICs, and they offer different speed and power and cost trade-offs. And then we had spent a little time talking about that, how the cost trade-off is a little bit trickier, because this has to do with the way electronics gets manufactured, namely there is a non-recurring part and there is a recurring part, non-recurring being the design cost and the tooling cost and things like that. Just to put in perspective, when you make a chip, for example, then to be able to make that chip, you need masks, and then using lithography, those things are made. Those masks run to around $1 million+. Okay, so if you're making a chip at small quantity, you still have to pay that cost. So, and the same way it's for EDA tools. Industrial quality EDA tool is like 100 grand plus per year. So these things can be a significant cost structure. On the other hand, you have recurring cost, which is for every part that you're making. And it's a trade-off between the two which makes the cost interesting. So going back to the slide, because microprocessors and MCUs and all are high volume product, the non-recurring cost becomes kind of a tiny part of the cost structure. And on the other hand, for if you're making one-off, which would likely be the case with, let's say, ASIC, where the volumes would be smaller, things kind of go in a different direction. So, so that was something we discussed. And then processor versus microcontrollers. Microcontrollers being the one we are dominantly using in a lot of embedded systems. The Hexaware platform itself, so you should have adequate familiarity with it. That's the expectation. Just to rejig your memory, so Hexaware itself has 2 MCUs in it. There is a K64F, which is kind of the big MCU, and that one is what you program when you're writing an embed application. And then there is the other tinier KW40, which has the radios built into it, and the other thing it has is also the touch buttons, the 6 buttons that you see on the screen. It's something that will actually get to face when you get into Bluetooth programming. All the other sensors are attached to the main MCU through various means, various buses and things like that, and so there is a whole slew of sensors attached to this. If you're not expected to know kind of the data sheets and all, obviously, if I would have any question around this, I would provide the requisite numbers. Okay. Likewise, if I'm going to ask anything about which requires embed code or something, I'll just give you the API calls. Okay. But I do expect that you would be able to write C, C++ code given the API calls. Again, nothing very elaborate, but you should be able to spot problems with the code structure, being able to fix it, those kind of things. Okay, so the intent is not to write a whole program, but intent is you should be able to identify issues that occur in the code and be able to write like small snippets, like 1 or 2 lines kind of things, fill in the blanks type stuff. Okay, so just as an aside, not for the midterm, on the Bluetooth side, what happens is there is firmware running on this KW40Z also. So this is this is where embed. This is what embed software goes, and this is not embed. Okay. Now, when you get Hexaware, both of these come with some factory firmware, and when you if you don't set the switches correctly, so those 8 or 9 dip switches, 2 of them control whether you're programming the K64F or not, and another 2 control whether you're programming the KW40 or not. We have, to be able to write firmware for this KW40, you need kind of a separate tool chain. It's not something that, to the best of my knowledge, embed has targeted. Now, the Bluetooth sample that I circulated some hours ago, basically what happens is that someone, Hexi people, wrote the firmware for this thing, and the source code is on GitHub, so you can kind of look at it. Its capabilities are exposed via an API over this serial link. The serial link is both UART and I2C, so I don't know precisely which one they use, but that doesn't really matter. So someone has created a class on the K64F which hides the details. So all the Bluetooth protocol is kind of handled by this guy, and then it provides hooks through that class, which is exposed to a library in turn, to be able to attach callback functions and all, so that this can do its job. So we don't mess with this, although in theory it's possible by messing with those switches and all, you may accidentally wipe off the firmware on this one. So, but as long as you are carefully following the instructions, that should. So the example I circulated, the example I circulated shows shows how to uh, do two type of things. Number one, um, send sensor data. So it turns out the firmware here is designed so that when some party, let's say a phone or Raspberry Pi, requests certain characteristics, certain attributes with sensor data, then in turn this asks this guy, and then there is a callback function you have to write. So you say temperature data is this. Okay, so that example shows that. And then also there is a catch-all command this guy, the firmware here offers, so that you can send a control command. So there is a provision that you can send a control command to Hexaware, which in turn results this guy resulting in a callback out here, and then you can write that function. And the example we have is that callback results in the LED toggling. So, so that's the structure. So you will never directly kind of deal with the BLE protocol because that's kind of all fixed. So that's a side note. You don't need that for midterm. Another thing that we covered was the power management in computer systems, and a few concepts that we had. One was the fact that MCUs and in general various components that you have in embedded systems, they tend to have multiple power modes, some sort of active mode, some sort of idle or sort of kind of mode, and then of course you can power things off in many cases, and this is something you'll find in CPUs, peripherals, whatnot. In particular, the Hexaware unit has a whole bunch of different sleep modes. You save power by changing modes, and this thing kind of is referred to as dynamic power management. That is based upon some criterion. Like for example, if your software has nothing to do and you expect that it will not have anything to do for a long while, then maybe you would save energy by switching to some sort of a lower power reduced functionality mode. We also talked about frequency scaling and frequency and voltage scaling as two additional things. So while in the active mode, you can change the power performance by doing either frequency scaling or voltage and frequency scaling. So one thing that I had shown in the lecture notes was that the power tends to be proportional to V square F. And moreover, you can say delay is proportional to F inverse, right? So these two facts come into play. So with frequency scaling, all you do is you change the frequency. That affects the delay, and it also affects the power, but it affects them proportionately. So energy, which is equal to power times delay, remains constant, right? So when you do frequency scaling, you are not really gaining anything in terms of energy, but you are reducing the power footprint and the cost of delay. And this in itself has uses. For example, maybe your battery is incapable of supplying the right amount of current, or maybe heat considerations come into play, but it's not going to the first order. It's not going to affect the lifetime. Actually, it turns out that there is a lifetime impact also. When you draw current at a lower level, then you can make the battery last. You can get more energy out of the battery. But ignoring that, if you think of battery as having certain amount of energy, this thing doesn't help on the energy front, but it does help on thermal and peak power. But if you care about energy, then the game switches to voltage and frequency scaling, and this is where V squared term comes into play. So loosely speaking, there's a relationship between delay at the transistor level, at the gate level. Delay is, to the rough order, you can say, is going to be proportional to 1 over V to the power some alpha, right? The higher the voltage, lower the delay. And again, not strictly true. It's a very complicated expression. So this is a very crude thing, but they go in the different directions. So what you could do is as you are lowering the frequency, you can also reduce the voltage because you don't need as high a voltage, and therefore you end up with kind of perhaps a cubic type reduction in power. Some constant. right?
Is this to indicate how much frequency and voltage together is being reduced?
Yeah. So usually this alpha is going to be somewhere in the neighborhood of 1, okay, approximately, right? So it's basically saying that as I reduce the frequency, I can get away with slower hardware, and slower hardware means hardware running, I can therefore run the hardware at lower voltage, okay? There are, of course, limits because I can lower the voltage in the middle of the hardware, but outside world still expects me to speak at a certain voltage. So you can't do this thing arbitrarily, but that's kind of the intuition out here. So in voltage frequency scaling, we adjust both these knobs. And what that does require is some way of controlling voltage under software control. And that oftentimes is done more at the board level as opposed to being provided on the chip, although our chip does seem to have some limited form of this. Frequency scaling is almost always you will find within the MCUs that there would be some software register through which you can choose to operate it at a different frequency. Then we had talked about that this energy versus power distinction comes in another way also, which is complex processors tend to be architecturally complex. So therefore, while for doing bulk computation, they are very efficient. It's on the penalty you pay is that when they're idle or even perhaps in some sort of a sleep mode, just because they have more transistors, they burn more power. So we kind of saw this thing that between some 32-bit processor and some 8-bit processor, you see that when it comes to doing active tasks, the 32-bit stuff is way more energy efficient, takes a lot less energy than the 8-bit stuff does. And that's simply because the 32-bit things have firstly it's doing 32-bit arithmetic. So for doing sort of floating point and 32-bit integers and all, the 8-bit entity will have to approximate stuff to do it in software, whereas the 32-bit processor can race through it. And then the 32-bit processors tend to also have pipelining and caches and things like that, all the stuff which kind of helps improve the performance and so runs things more rapidly and therefore it wins out. But the penalty you pay is that it's very hard to make it go to sleep, come out of it. So we had these numbers where during the sleep mode, it consumes a fair amount of power and it takes a fair amount of time to wake up and fair amount of time to sleep. So in terms of being able to duty cycle, put things to sleep, power manage, the little processors tend to win out. And it's the game between the two that one has to face. So one way of thinking about it, it plays into your choice of processor, right? Depending upon what your workload is. But a more general framework to think about this is, and this is the concept that I talked about, energy proportionality. It basically says that given the system that I have, I would like the power versus functionality profile or power versus performance profile to be kind of linear. If I don't ask the system to do anything, it better not consume any power. And if I want the system to do increasing amount of work, howsoever I define it, then I want it to take correspondingly, proportionately more power. And this kind of burstiness in workload is something that you encounter in a lot of systems. A lot of times they're doing nothing, and then suddenly there's a burst of activity. And you want to be able to do it. Now, the reality, unfortunately, is that most of our systems, when you look at their performance versus power curve, they kind of look like this. They have a big initial offset. That is simply the baseline cost you have. And this offset is smaller for small simple things and is bigger for bigger things, right? I mean, if you have a server, this offset is going to be huge. If on the other hand you have a tiny little Raspberry Pi, this offset is going to be a lot smaller. So that led to this notion that perhaps we can fake energy proportional systems by stitching together many different systems, each one of them optimized for different part of this curve. So I can have some simple or some specialized stuff which which is very efficient at one end. On the other hand, I may have a bigger processor which is operating at a high end of the performance range. And within each one of these, we may have dynamic voltage frequency scaling and other capabilities out there.
Which coupling is a different microarchitecture?
So it's basically saying tight coupling means I have two processors of the same instruction set but different implementations. Okay, so the same program can run on the both, but presumably with uh, different performance characteristics. So in this case, I have two cores. Both of them are, let's say, ARM, or both of them are Intel. So they have the same instruction set architecture, but they may have one may be pipelined, or they may have different types of pipelining or different amount of cache. So they differ in their realization of that instruction set architecture. Whereas loose coupling means something totally different. It would be an 8-bit microcontroller or something. And by creating these assemblage, you kind of fake an energy proportional system. So this is one of the ways you can fake energy proportional system. Another way is to have a large number of identical systems and then keep and change how many of them are up. This in effect, this works well when your workload is far more than what a single unit can handle. So for example, let's say you are in the business of doing providing a signal processing service or machine learning service or database search service. You may increase the number of servers that are being used as the workload increases. So typically, so the other way of faking it is to have large number of units, and you keep some fraction up. So one is this, and the other is kind of this large bank. And you would find this kind of approach perhaps more common in cloud services and all, but you could imagine even in embedded systems to some extent they are there. So nowadays we hear about octa-core and these kind of processors being used on edge devices, and there you can play this game of whether one processor is up or all 8 are up depending upon the workload. We had also, in this context, the big.little example from ARM, that how in many chips now you see two versions of ARM being combined together on A15 and A7. They are both A series processors, so they offer the same instruction set architecture, but vastly different operating point. And then through the operating system, you kind of switch back and forth between them. And we had presented some simple example of what that switching policy might be. For example, you can monitor the workload, and if the workload is exceeding some threshold, then you switch to the big processor, and vice versa. On Cortex, which is what Hexaware has, is not identical in terms of ISA. In particular, it lacks a lot of capabilities that these two things have. So that would be an example of a heterogeneous or loosely coupled processor. So you would find systems where there may be Cortex M3 or M4 or some Cortex M series processor together with something like this. Your iPhone actually is a good example where some of the workload is handled by Cortex M series processor, not programmable by you, but Apple kind of uses it that way. Okay, so big.little and sort of this way of straddling things, and kind of the other approach, which is large number of units. Yeah.
Is big.little just an example of a method doing trade coupling?
Yeah. Yeah.
And
Big.little is actually what ARM calls it, so it's more of a commercial jargon. Yeah. Okay.
So can big.little implement loose coupling as well?
Can big dot little implement loose coupling? Big dot little itself doesn't, but a lot of companies who make chips using it, they often put a Cortex M also in a loosely coupled manner.
So it's basically you trying to do the same thing and just doing it differently.
Well, no. So they'll have a big dot little cluster and a loosely coupled cluster. Okay.
And DVFS is just an additional method.
DVFS can be applied to all of these. DVFS, DFS, and shutdown applies to all of them. So it's orthogonal. Okay. So within each one of these bands, you may have DVFS and DFS. If it is DFS, in terms of energy, it would remain flat, whereas if you have DVFS in terms of energy, also it will scale.
So this TI OMAP in itself is like a big argument, right?
Actually, TI OMAP actually has the whole thing. It also has a loosely coupled cluster, also, except that in that case, this guy is not an ARM, it's a DSP. Okay, so it's TI's own processor. But TI OMAP is an example of having a whole bunch of things going on there. Yeah. Okay.
What
Yeah.
is loose coupling and tight coupling?
So tight coupling means processors are usually share memory operating off the same RAM, and very importantly, they have the same instruction set architecture. Okay, so you can literally take the same program, run it, no problems. Okay, loose coupling means that there is firstly, the communication bandwidth between the two might be more restricted, like there may be some specific area of shared memory or maybe some sort of a queue between the two, as opposed to whole memory being shared. But more importantly, their instruction set architecture may be entirely different. So like one may be a DSP, the other may be a ARM processor, for example. Okay, in which case you can't simply move the program from one to the other. You have to have different versions of the program and then think about how do you do the state transfer.
Thank you.
Okay.
So for DB, dynamic voltage frequency scaling is tight coupling.
No, again, so that was a question that Aditya was asking also. It's an orthogonal dimension. Each one of these processors may have DBFS.
Oh.
Okay. Each one of so you can say these processors define kind of broad areas of operation, and within those areas you have some level of scaling going on, which could come from DBFS or DFS or some such mechanism. Okay. So at the end of the day, your goal is, again, to kind of rehash that point, energy proportionality. The more I want out of the system, I want the system to scale gracefully. And then when nothing is happening, kind of really die down, okay, in terms of power. But given that our components tend to be not energy proportional, you have to, in effect, fake this thing by playing these runtime games. Okay, another thing we had talked about was I/O. We spent quite a bit time on that. So first thing we had talked about was that how I/O is done in kind of two very different ways. One is specialized I/O instructions, and Intel processors are examples of this. So we are not using them, but nevertheless, and they reside kind of in its own separate address space. They call them I/O ports and things like that. More common, particularly with ARM processors, is that the I/O is just part of the regular memory space, and you use just the standard instructions to do it, except that now you may have to tell the compiler some additional hints like it cannot cache this stuff and all. Okay, so you have to you have to make sure that the compiler is aware that this is just not a regular area of the RAM, but rather it's an I/O device and takes some careful accounting of that. So that was one part which we had covered, and then we had gone through various kind of I/O examples. Yeah.
Like the concept of memory command I/O, like so, is this like some GPIOs are attached to that register inside?
Yeah. So there would be some register where the processor vendor would give you some way of saying, if you write a 1 here, then the pin would be treated as an output pin, and then if you write to a different bits, it will say what bit is being written. How those details are done depends upon the processor, and I think would be instructive for you to, for example, not for the exam, but just generally for the processor we are using. If you go to the data sheet, you'll find that they describe that, right? I mean, each pin is configurable as an input pin or an output pin or both, okay? The so-called bidirectional pins. And then additionally, there's a set of registers by configuring it. So you first, upon boot up, you configure what kind of pin it is, okay? And then the next thing you do is, if it is output, you're going to write something to it, default values basically, set them up. So those registers are the ones which become memory mapped, okay? So when we say IO is memory mapped, we don't mean the pin is memory mapped, because that doesn't mean anything. It's the set of registers which are controlling the pins are memory mapped, okay? And likewise for timers and stuff like that.
Wait, wouldn't in the other way, specialized IO, wouldn't you also have registers there?
You have registers there also, but except that they are accessed through special instructions. Okay. So firstly, at one level, it makes the compiler job kind of a bit more difficult. It has to know about two sets of instructions, but it's also ugly. I cannot, since these are special instructions, I cannot think of them as data structures in memory. Okay. So the IO kind of gets kludgy a little bit there. Here, those registers are just residing in the regular memory space, so you can think of them as a data structure, and you have a pointer to a particular physical address, and then you can use your regular C language instructions, whereas here you can't. But if you are accessing those capabilities through APIs like the Mbed API, then it doesn't really matter to you, right? I mean, at the level of setting a digital pin, output pin to a value, Mbed hides these details from you. Now, having said that, Mbed is only ARM, so it doesn't really matter. But let's say Mbed were to be ported to Intel, it would have hidden those details from you. But those who are writing the operating system, for them these details matter.
And also, like, chance of memory corruption in that is because of accessing these IOs. Like, sometimes you access out of bound memory errors because of you writing within the same memory also.
Okay, so very important. You don't get out of bound memory problems in our systems because there is no memory protection. Okay, but you're right that if you were to be doing it on processors which have memory protection, then you would get an error. Actually, our processor also does have memory protection of a simpler variety. Basically, you can designate areas of memory which are read-only or write-only. So it doesn't have the kind of stuff that A-series processors or Intel processors would have, where you have pages and every page you can configure who can access it. There is a limited form. Mbed doesn't seem to use it, but let's say you could sort of on top of Mbed directly create those, and in which case you will get an interrupt. Okay, and then how you handle that interrupt is up to you. Okay, so when you do an invalid thing, then it's basically causes the hardware to throw up interrupt.
So if there is no memory protection, it
Then
just
nothing.
stays
Something will get trashed. You will never know. Its effect may get known later, like your car crashing. Yeah.
In both the approaches, there's some sort of protection mechanism that you mentioned, right? For the first one, it's like kernel nodes or whatever. What would
Yeah.
be the different?
Yeah, so in this case, so again, the example of this one is Intel, and Intel processors really are kind of higher end processors. So they have rings and only kernel mode. In this case, you will have to make sure that anything that you are protecting resides in a area of memory which only the kernel can access, if that were to be your structure. Okay. So there would be some provision for doing it. So for example, again, Mbed doesn't do it, but the processor, the K64, has these ability that you can specify a small number of regions in memory where you can say it as read only or write only, and so you could protect that way. Again, emphasize Mbed doesn't use it. So there are general purpose IO pins, which are basically digital pins, which are either input or output or both. And Mbed, in our case, provides a very stylized API for doing it. So it's a lot of it is hidden from you. And likewise, actually on Raspberry Pi, there is a set of instructions, there are well-defined API to These are pretty powerful. You can use them for also debugging. We use them for generating PWM waveform, for example. You can use them for debugging and stuff like that. Okay. So that's the GPIO pins. Oftentimes, the pins on the processor are multi-purpose. So again, there would be some register via which you would be able to specify what is it for. And then we have analog pins, which are the counterpart. They come in two varieties, those which are analog input and those which are analog output. Analog input means that there would be some sort of A to D converter, and analog output means there would be some sort of digital to analog converter. And a point that I made was that usually multiple pins share a same ADC, and then you kind of rotate, multiplex them. Whereas for DAC, you can't really do that because it has to drive a pin. So if I have two analog output, I will need two digital to analog output. Another aspect, a couple of things that come into play out here is bit resolution. How many bits you have, that in effect tells you what's the quantization error. If I have an 8-bit analog, then that means I am dividing whatever voltage I have by 256 levels. So that's telling me the resolution of the signal I have. So it's very important that you would match your analog input to the range you have so that you make use of all the bits. So if your analog signal goes from 0 to 0.5 volt and your ADC is designed for 3 volt, then you better have an amplifier which makes scales 0.5 to 3 so that you make use of all the bits. Otherwise, you are effectively using fewer bits. And the other part was sampling. You can do asynchronous sampling, which is basically read on demand, or you could do periodic sampling, in which case some sort of a period based upon some sort of a period that you would do it.
How is the arbitration in the multiplexing done? Like, if I have all the 4 input pins being by
So in case of asynchronous, you would simply say, I want to read from channel number 1, channel number 2. In case of periodic, you are going to usually, the mode is that processor would let you tell which channels are active, and then it will keep rotating. Depends on parameters. Now, question for you: what rate would you sample an analog signal at? Nyquist rate, right? And which is what? Twice the frequency, twice the maximum frequency. So that was this. Now you are going to do that if your goal is to reconstruct. So the main point is, if I sample an analog signal and then I have these sample values, then under a very specific condition, namely that my signal was band limited, namely its highest frequency was less than half the sampling rate, then I would be able to, on the digital side, reconstruct the waveform. Another way of saying is that if you ask on the digital side, what is the value of the analog signal at some arbitrary point in between the samples, I can compute it. There is an algorithm for doing it, which relies on using sync functions as kind of a basis function to doing the interpolation. But very important that it be band limited. How do we make sure that the signal is band limited? You do it by putting in a filter. So let's say you are sampling at a particular rate, then there would be on the analog side some filter which is going to strip away the high frequencies. And then after that, rest of the A to D conversion happens, which involves sampling the analog value and then converting it into a set of bits. So your A to D converter does these two parts: sample and hold and quantization. And then finally, there is some digital encoding that gets done. There are most of the time you just do a linear encoding, but there are some A to D converters which do some warping also. But eventually you get digital bits out. Very important part about aliasing, that what happens under the hood is when you are sampling, then if you look in terms of the spectrum of the signal, then sampling basically corresponds to replicating that spectrum at the same at the sampling frequency. And if the spectrum, so what's happening is that as I am sampling, then originally this was my spectrum, okay, and then this is Fs, this is Fs. So basically the act of sampling is kind of replicating the spectrum, and if my spectrum is such that the uppermost frequency is less than Fs over 2, then the two are separated. And if the two are not separated, then you have irretrievably lost that information. So very important to do it, because you can't undo it on the digital side. So it has to be done on the analog side. And usually not an issue, because there are always some filters out there which do it. Another one we had talked about was PWM, which is another way of doing analog output, except in this case we encode the analog value in time. In particular, we encode it in the ratio between some period and how much is the signal high for. So for example, we'll select some interval. We'll say I have a periodics. I'm going to do a periodic waveform at, let's say, 10 milliseconds, and then the fraction of time for which the signal is high indicates the value relative to 1. So in this case, we are saying that, look, whatever is the maximum analog signal, I want my output to be 75% of it, with a waveform, 50% of it. And the way we achieve this thing is that we feed this waveform to this kind of a structure, which basically to my target system, in this case an electric motor, I'm basically applying some voltage V plus, the fraction of time for which my PWM was high. So if the PWM signal was high for 50% of the time, then 50% of the time the current will flow through this thing. And that in effect means that I'm applying that ratio 50% times V plus. In this example, for example, let's say V plus was 12 volts. I believe that's what this example is structured for. So 50% would mean I'm applying 6 volt average. Okay, so I'm just I'm multiplying my peak voltage by the fraction that the PWM is specified. So what do you see are the trade-offs between PWM versus A to D converter when it comes to doing analog output?
You need specialized hardware there. Here you could just probably even get it out of.
Okay, so standard digital hardware. So that's the pro for PWM, right? I mean, I just need the standard timers and all. What's the negative? Hmm? In ADCs, you mean? Oh, yeah, in DAC, you can control resolution. Yeah, I guess you can control resolution here also, except you're controlling it via time. So the resolution here would be the number of bits in the timer. Okay. In fact, you can probably control the resolution very well out here. The problem here is a period. Okay. The sampling rate can become a bottleneck in this case. You may need very fast counters, which can be a problem. So like, for example, let's say I have an A to D converter, which is or D to A converter, which is 1 mega samples. Okay, so every microsecond, I'm outputting a new value, right? So I can change it. In this case, and let's say it is 8 bits, right? So now that means that I need 256 times 1 megahertz to be able to do it with PWM, because if I have to change the value potentially every microsecond, then that means I have to have a counter, 8-bit counter running in that 1 microsecond period. So my counter would be running at 256 megahertz, and that's a simple example if it was 12. So getting the same temporal resolution can be a tricky thing with PWM. But it's used for LED lights and motors and stuff like that, where the dynamics are much slower. They are in milliseconds or tens of milliseconds. We spent time on serial interfaces for MCUs. Yeah.
So the sample rate is a major bottleneck, right?
Yeah, sample rate is
can be achieved, but
right. So resolution can, because you can make 32-bit counters. In fact, you cannot make 32-bit DACs. Okay, easily. I mean, that's a lot of resolution, right? The problem here is the sample rate. Serial interfaces, so we had talked about a whole bunch of them, but primarily UART, SPI, and I2C, and I think 1 or 2 others. They are all at some level similar. You should have some rough familiarity with the differences between these, like one-to-one, multi-master, what role stop bit, start bit play, stuff like that. Okay, how are we doing on time? Almost. Okay. Software organization. So we talked about organizing firstly, kind of the whole notion of concurrency. And you saw that in the homework also, which is trying to do multiple things simultaneously. That's how do you structure your software to do that. And we saw different ways of doing it, but ultimately, all of this boils down to is how do you handle events at some level. So one thing that all MCUs, all processors provide is the concept of interrupts, which at the hardware level, you have a hardware event, and when that hardware event happens, then the processor stops doing whatever it was, and it goes into the special interrupt mode, and it calls a function there. And since that may happen at any arbitrary time, so it's important that this routine, which is handling the interrupt, should take care that the functionality of the main software which was running is undisturbed. That means any register it uses, its value should be unchanged once it is done. So one of the important ways an ISR differs from a regular function is that ISR has, when it returns, the state of the processor should be unchanged insofar as registers are concerned. Okay, because otherwise the impact would be seen by this guy, by the background process. Whereas in a regular function call, compilers decide on an agreement that what registers are going to be preserved and what can be trashed. Okay, every compiler has its own details, not decided by the hardware, but the compiler makes sure that there is a well understood protocol that caller can rely on some registers not being disturbed, and the callee, the subroutine, is free to mess with other registers. So, and then at the hardware level, if there are multiple sources of interrupts, then again the hardware would have some sort of an arbiter which will map different interrupts to different interrupt service routines. So it's taken care for you. With a system like, with an OS like Mbed, what happens is you are writing the ISRs, except what's really happening is that there is a wrapper around them which Mbed provides, and then it calls your interrupt handler. And what are the things we cannot do in interrupt handler? Hmm? Okay. Anything which takes a long time or potentially can block, right? Printfs, why do printfs take a long time? Right, so what part is slow then?
The buffering to the output.
Yeah, because they are sending stuff over a serial line, right? I mean, and the serial line is slow, like whatever, right? And in fact, but that apart, printfs also have to do all this formatting and all, and even that takes time, okay? So the first cut optimization for if you want to do printf is to use printf, which is write to a string, and then put that string into some sort of a queue, and then some background thread can handle that, okay? So in general, that's the other thing with a pattern that we saw, that you do quick and dirty stuff in the ISR, and anything which needs long handling, you put it into a queue or some other structure. Mbed provides a very nice queue abstraction, and let a background task, perhaps a thread, handle that. Okay, so we saw in the lectures one paradigm where ISR puts it into a queue, and you can have one or more threads which are the worker threads, and they kind of pick an element from the queue and kind of handle that. So let's say, for example, our ISR was taking speech samples from a microphone, and then we want to collect a bunch of the samples and then do an FFT or some other processing on it. So that would be kind of the logic that you would follow. Even in our case, when for the homework, that was a possible paradigm to use as well, which is you take the user input and sort of read it in the ISR, and then let the actual task work be done in the main processor. So very important to keep the ISRs sweet and simple. We talked about different ways of organizing the.
I have a related question.
Mm-hmm.
What's the difference between exceptions, traps, and software interrupts?
They're basically the same thing. Okay. So trap is an interrupt which the reason I'm pausing is the following, that some of this jargon gets used multiple ways. Okay, so in case of Intel processors, For example, trap is something which is generated by making a call to a particular instruction, and then the effect of it is much like an interrupt. Okay, but in particular, when that is happening, the other side is inside the kernel. So the trap is used for system calls. So you make when you make a system call, you're actually generating a software interrupt. Exception gets used multiple ways. So one is in the same sense as traps, but the other thing is also many programming languages provide you an exception abstraction, which basically says I have a piece of code and something nasty can happen anywhere and I want to just jump out of it. That has nothing to do with interrupts. That may be entirely a programming language thing. So like for example, many languages, Python, Java, they all have some structure like try and then a block of code and then except, right? I mean, in that case, basically the idea is instead of sprinkling if error, exit or do something every place, you basically can let the error happen any place and then have a clean exit.
The ones that divide by 0.
Okay, yeah, so that's why I said those kind of exceptions are handled at the hardware level. So if you attempt to do memory protection violation or divide by 0 or anything which at the hardware level is illegal, then it's also called an exception, but it's actually just an interrupt. Okay.
Like so, if something encounters divide by 0, just like
an interrupt would be raised, or even worse. I mean, you attempt to on our bigger computers, memory DRAMs are often parity checked, and you read area from the memory, and it has a parity violation, then it will barf and give you an exception, and then that results in kernel panic. Okay, so yeah.
What does that mean? Maintains interrupt flags to allow polling as well, the last line.
Okay. What this is saying is the following, that when an interrupt occurs, then usually in most of these processors, there would be some register where the fact that that interrupt line was active is asserted. So one of the modes you can operate in is you can disable the interrupt. Okay, and then basically poll those lines. So let's say you wanted to be interrupted whenever the signal went high. Okay, the edge. So the occurrence of the edge would cause this flag to be set, and then you can, instead of having an ISR, you can poll for that poll on that register. Okay, so that's all it is saying. Okay, so let's see. We can organize for purposes of concurrency. There are various ways we can approach this from a software perspective. So we can stick with subroutines, which are hierarchically structured. Subroutines are software modules which you enter and exit, and the next time you enter in the same place. So this thing works very well with callbacks and event handlers and those kind of things. And then on the other extreme, we have the threads, which basically give us the abstraction as if it's a program which is always running, and if it exits, it will re-enter wherever it left. And so we kind of spin off these threads, and they can last forever until the system dies, or if they exit, then the thread is killed. And then there was this coroutines that I had introduced, which have the property, which are kind of shared properties of both. So like threads, when they re-enter, they start from where they left off. But like subroutines, they all run on a single stack. So they have efficiencies of subroutines, but kind of give a concurrency model which is kind of more thread-like. And in many languages and many systems, this becomes kind of an attractive way that you retain kind of the friendliness of thinking in terms of multiple sequential activities which just coexist, but you get the efficiencies like subroutines do. Now Mbed doesn't provide it, but you can create a coroutine model in Mbed pretty easily. There are packages which kind of let you do that on top if you so wish. Okay, so we spent some time on kind of this thread versus event way of thinking of tasks that we are doing. So in both cases, there is a kernel. In the kernel, there is some sort of a queue, and in that queue, every time some event happens, either a hardware interrupt comes in, and the interrupt handler does something, or maybe one of the current tasks does something, it goes into that queue. And then the kernel basically loops through the front of that queue saying, is there something to do? What's the next thing? So when a timer fires or things like that. And in one case, what's happening is like a bunch of threads, and what the kernel will do is it will restart that thread. And so the thread will restart wherever it had left off. Whereas in the handler model, each one of these handler is subroutine, and so you call that subroutine. And if it was a coroutine, then it would be kind of a hybrid, okay? That is, within the coroutine, the flow goes like this, but they're still sharing kind of the same stack. Embed threads in embed, an important point is that they yield back to the kernel only when they make one of the embed calls. So they are not fully preemptive. That is, the kernel cannot bump up a thread anywhere. But in a fully preemptive system, what may happen is, let's say the middle thread was running and it does something. It emits an event, and that event causes thread number 3 to be activated. Then immediately, as soon as it emitted the event, it will switch control out here. Or for example, let's say an interrupt handler comes in and the interrupt handler does something. So thread number 2 was running, and then the interrupt comes in, let's say some serial port interrupt, and so we'll fall into the ISR. In the ISR, some event is generated, which now makes thread number 3 active, and let's say it has a higher priority, then immediately we'll switch to thread number 3. So embed has some limitations in this regard, but it is otherwise the leftmost model. But you can always write the right model with embed also. All you have to do is make sure you have a single thread, and then you write in terms of these. So if you have a threaded system, you can always use it in the mode as if there was a single thread, and then kind of write in terms of these. So we had looked into kind of 3 ways embedded software gets organized. So single task, where basically I have it's as if even interrupt handlers don't exist. All I have is a loop, and in this case, I'm going to poll for events, and then based upon that, decide what I'm doing in the loop. So I'll just repeatedly keep doing it. Foreground, background tasks, we basically have, again, a background process always running, and then we have interrupt handlers. So whenever the interrupt happens, the ISR runs, and then it would take care of the time critical stuff, and anything else which is more delay tolerant, it will set a flag or put something into the queue, and then the background task is going to pick that up. And then finally we have multitasking, which basically is another way of saying is that I have multiple background tasks of different priorities. We still have the interrupt handlers. But by the time usually you come to multitasking, you end up using an operating system of some form, embed type things. The kind of operating system that we are using, embed and all, a term which is used for them is called library operating systems, because they are really glorified software libraries. Okay, they are very distinct from Linux or these kind of things where there's a whole bunch of other stuff which kind of goes on. So those are the 3 ways. This is an example of a foreground background one, where interrupt does kind of a time critical thing, and I have a background program which is kind of just spinning, and it says if time for display, do something. So instead of doing a bunch of delay tolerant type of things, and it's possible that foreground, the interrupt handler may put tasks for this guy to do into the queue. So what may happen is the foreground interrupt may handle the time critical stuff, and non-critical stuff puts into the queue. And here, instead of saying while 1, you will say while the queue is empty, wait, and then when the queue is non-empty, handle that and then keep processing that. So kind of a very typical pattern. That worker model, which I shown in the lecture, once fits into that category. We had talked about how embed OS looks, but that's very typical of any such multi-threaded operating systems. In a sense, I have threads which reside in one of some states. Basically, one thread would be running. Then, when the thread needs something and is unable to run anymore, like for example, is waiting on a semaphore or waiting for some signal, then it's moved to a waiting status. And then at some point, the necessary event occurs. Then the thread gets ready and it's put into the ready queue, and then the operating system makes sure that one of those threads is running. Specifically, in case of embed also, is the highest priority thread which is running. And then when the threads exit, you kind of get put into the inactive state.
It's an event that switches from waiting to ready or waiting to running in itself, an interrupt that tells that your resource is ready or your priority has been pushed to a higher level. Is it like that, or?
So interrupt would do something which will cause the OS to realize it. Okay, so essentially what happens is that there would be some select interrupts which as part of those interrupt handlers take care of messing with the operating system. In particular, there is a system tick. So whenever the system tick interrupt occurs, at that time it goes around checking what is happening in the OS, and it goes to the OS data structures and do it. Your other interrupts that are occurring at those points in time, rescheduling event, I'm not sure, but I don't think that happens in embed. So like for example, I don't think the rescheduling would necessarily happen for an arbitrary interrupt pen unless you choose to invoke some OS function. So let's say, for example, you decide to bind an ISR to a GPIO. Then OS has no way of knowing. Okay, so it will only get to know when the next systic happens.
Okay, so it is only the OS, the events that are spurred by the OS that tell it to run.
Yeah. So here, what the event is really referring to is the OS level concept of event. It's not interrupt handler. The interrupt handler has to emit an event for this thing to happen. So there is a event generation command in embed, and the interrupt handler can choose to call that emit event, and then the operating system will know.
So that is a way of bypassing the OS.
You're not bypassing the OS. You are just telling the OS that I've emitted this event, and then whichever thread may be waiting for that event can run on that. Okay, we had talked about timing constraints. Firstly, we had talked about like how timing constraints come into varieties. Timing constraints on the performance of the system you're designing. Timing constraints on the system you're designing, and timing constraints on the environment in which your system is embedded in. Both are important because it's kind of like a contract. We are designing the system given some contract with the outside world. So both of them are important. And then the other way of looking at it was that there are constraints, max constraints, min constraints, and durational constraints. And then we had looked at kind of variants of these. So like we had the concept of stimulus and response. So you can think of your system as receiving stimuli from the environment, so things coming into the pins, and your system generating a response, which in turn is a stimulus to the environment, and the environment reacts and perhaps causes something, right? So for example, we see that the car is getting too close to the lane marker, and then that becomes the stimulus. Your system reacts, turns the steering wheel, and then the car moves next time around, right? So that's what's happening. So with that, we enter into all sort of possibilities, timing constraints which are between stimuli, timing constraints which are between a stimulus to a resulting response, vice versa, from a response to a stimulus. This one in particular is a constraint on the environment, because we are saying when I give the response to the environment, the stimulus from the environment should come within a certain time. Okay, so say that, and then response is between two outputs of our system. Think about it. You should be able to come up with examples both in the max and min and durational categories. And then the final thing that on the time side that we had moved to was how do we go around designing systems which meet these timing constraints. And in particular, we went after a very simple model, which is I have tasks. Tasks have instances of those tasks are arriving, and our goal is that we should finish them by a deadline. So you can think of in terms of as a stimulus response with a max constraint. So a stimulus arises, I have to generate the response, and I have to do it within a max. So in particular, our model was a bunch of tasks. They have periods. So task 1 has period T1, and so a copy of the task 1 arrives every T1. We do not know when it first came, but after the first copy came, subsequent copies will come in T1 apart, and likewise for T2 and so on and so forth. And so the phase refers to when the first instance arrives. Run times are given, C1 through Cn. These are worst case execution time, which we somehow magically know. These are getting these is hard, as we talked about, that they are affected by caching and voltage frequency scaling and all those kind of things. Deadlines are relative to when the task arrives, and very simple first cut model is that deadline is the same as the period, which is saying a task should finish before the next one arrives, next copy of the same task arrives. And then we have these other just like tasks can be bumped off at any time, and the OS takes 0 time. Is over at 0. And then with that, we had gone with this model that we are going to assume we have an OS which is priority driven and preemptive. So at all times, it will make sure, the promise the OS is making is, it will run among the tasks which are ready, it will run the one which has the highest priority. And then we had kind of 2 variants of this. One where the priority is fixed, that is upfront at the time we created the thread, we fix the priority, and we are not going to mess with those. And the second version is dynamic, where the priority of a thread can change over time. Okay. In case of embed, it's the latter. You can change it over time, but in many operating systems, it has to be specified only at the creation time. So scheduling problem basically boils down to then finding a way to assign priorities, because the basic scheduling otherwise is fixed in these things. And we had talked about that how, in case you have static priorities, then you usually run into situations where the fraction of the CPU needed by your task, the so-called processor utilization, may be less than 100%, but I may still run into deadline trouble. Okay, so if I don't assign the priorities correctly. So in this case, it turned out that if I assign the higher priority to the task which comes less frequently, we run into trouble. Okay, so that had led to kind of this whole intuition that how can I reason about a task meeting its deadline. So one sort of intuitive thing was that the worst case for a task is when it comes simultaneously with a copy of every higher priority task at the same time, right? Because all of those other ones will get the CPU before this guy gets it. So that's called the critical instant. And then the result is that if I give you a priority assignment, then one way of checking that I can schedule it is to show that every task at its critical instant meets its deadline, which is another way of saying is that the response time of the task is less than the period or less than whatever the deadline that we need. That led to a first cut priority. Yeah, go ahead.
The algebraic expression for that would be like even if the first priority task has like the rate of occurrence much faster than the least or the critical instant for the task which we are going to measure, would it be like n number of times the task would occur before this can actually get executed, or just the first request?
Okay, so the promise you have to make is that if the task whose deadline I'm worried about arrives at the same time as a copy of each one of the higher priority tasks, then this copy will meet its deadline. Okay. But what may happen is by the time it meets its deadlines, additional copies of the higher priority task may have arrived. Okay, because maybe my response time is too long, and so the high priority tasks may arrive multiple times. There is also a situation where if your deadline is more than the period, allowable deadline is more than the period, then you run into this issue that when you're looking at the critical instant, you're, just a sec, my battery is going out. Okay, so you kind of run into run into the situation where if I'm looking at a particular task and I look at its critical instant and I look at when this particular copy finishes, that may actually not be the worst case. I may have to keep simulating for additional copies until I may find a violation. So the more general rule is that start with a task arriving at its critical instant and then keep checking until you either find a violation or the task finishes and there are no more additional copies of this task in the system. So let me explain. Let's say I have a task whose period is 10 seconds, but allowable deadline is 15 seconds. And that's the task I'm worried about, right? So what may happen? I start looking at its response time, and maybe its response time is 13 seconds. Now the thing is, by the time it is 13 seconds, another copy of this task has arrived. And I now have to worry about that guy also. So I have to keep this process until there is no copy of this task in the system. Okay. It has to be the case that eventually that will occur, because otherwise I will keep piling things up, right? So eventually it has to be. So that's the most general situation to arrive. But thus far, if you recall in the course, we only considered cases of t equal to d and d less than t. So we never considered the case d is greater than t. Okay, but if you do have that case, then you will have to kind of simulate for a longer time. So we had this in the case that deadline is equal to period. We had this intuition-based priority assignment, which basically said more frequent the task, give it the higher priority. And it turns out that if my priorities are static, then this is the best one can do. Again, remember, this is for the case deadline is less than the period. Oh, sorry, deadline is equal to the period. So what this means is that I will give a rate monotonic assignment to the priorities. I'll give highest priority to the task which is most frequent, and the next one, and so on and so forth. And I'll see if it is schedulable. And if the answer is yes, great. If the answer is no, then there is nothing else can schedule it. Okay? Nothing else which is fixed priority can schedule it. And then we went on to a bit of a detour that for rate monotonic, is there an easy way to check for schedulability without doing that simulation? And it turns out there are a couple of rules that help out. So we basically say, look, we know the C's and the T's for each task. So what if I knew the total processor utilization U? And that resulted in this rule which says that if the utilization is less than equal to this, n times 2 to the power 1 over n minus 1, where n is the number of tasks, then it is schedulable. And for n equal to infinity, this thing is around 0.69. So this basically says that any task set where U, the total processor utilization, is less than roughly 69%, is always schedulable by rate monotonic. For n equal to 2, this number is around 0.82, 0.83 or something like that. And so for 2 task systems, if U is less than that, it is always schedulable. If it is more than that, then it may be schedulable. But one has to do some separate test for it. There was a better test which, instead of making use of just the U, makes use of the use of I, that is for each task separately. And this one works the same way. That is, if ui plus 1, the product over all tasks, is less than equal to 2, then the task set is scheduled. And let's say all of this fails, that is, the answer comes out to be no, then you have to apply that theorem 1, which basically says for every task, I'm going to look at the critical instant. Now, we do know that rate monotonic is optimum for t equal to d. So there is no reason other than, no reason to check for anything other than rate monotonic. But except for every task, you have to do this thing. And in fact, you have to be very careful about this. You can't simply do it for the least priority task, because a common mistake one might make is say, if my least priority task is schedulable, then everything above that would be schedulable. That is not true. Okay, you have to check for everything. So that's an important point. And then what we had done was we had come up with an expression for the response time of the ith task, which was in terms of the response time of ith task will include its own computation time plus computation time for every copy of the higher priority task that I have to cater to. So the expression looks like the top one over here, and then we solve it using a fixed point thing, starting with some initial values for the response time, which the nice thing is this is a very nice function. It always increases. And we know that Ri is at least Ci, so a good first cut assignment would be make Ri equal to Ci, and then do the fixed point expression for every I. And finally, if my deadlines were not equal to period, but instead deadline was less than period, then basically your rate monotonic becomes deadline monotonic. That is, we look at di and give priorities according to those. So smaller the di, lower the priority. And you can see that d equal to t, the two cases become the same. Okay, so, and I guess the final bit we had was dynamic priority. What if priorities are dynamic, which in case of embed is possible? Then it turns out earliest deadline first, which basically says that at any given point in time, the task which gets the highest priority is the one whose deadline is the closest. This is very important. It's not saying that whose DI is the lowest. It's saying which needs to finish closest in terms of the wall clock time. And intuitively kind of makes sense. The one who's most urgent, I'm going to do that. And it turns out that for the case of D equal to T, Di equal to Ti, as long as U is less than equal to 1, EDF can do it. For D less than equal to Ti, there is again a simulation type process. I didn't go into it, you don't need to know it, cover it in so one has to kind of simulate in that particular case. Okay, so that was on the timing constraints. And then I guess the last week we had begun to go over wireless technologies. So we had looked into abstractly how radios work. There are various critical pieces to them. One is this medium access control, which is kind of an arbiter, which lets radios share a channel. And then there's a transmit pathway, which is encoder, modulator, convert to analog, boost the frequency, and then send over the antenna. And the receive pathway, where you amplify the incoming signal, the signal decays over the wireless channel, and then you lower the frequency, convert to digital, remodulate, decode, and how does the signal strength decay over a wireless channel? When I send out an electromagnetic wave, how does it decay? This is high school physics. Free space, how do signals decay?
They bounce off
No, they bounce. Let's say it's open space, line of sight, distance square, distance square, right? Inversely, it's 1 over d squared. Okay. Okay. It turns out that now world is obviously not free space, so a more realistic model, the fully realistic model would be what Nithya was saying, which is signals bounce around, and also I can do some simulation where I can look at radio waves and then see how they're bouncing around, worry about material characteristics and things like that. But it turns out that kind of a first order abstraction which is often used is we basically say instead of d to the power 2, maybe it is some higher coefficient. So it turns out in urban areas d to the power 4 or 5 or 6, something of that order works pretty well. And then another game we begin to play is we say that the factor in the numerator, the constant term in the numerator, is not really constant. It stochastically varies. Okay, so it's a random number with some mean and variance. So these kind of crude first cut models are often used to be able to say something about how the channel is behaving. So for example, this takes into account things like you enter a parking lot. So just a tiny transition, as soon as your car enters the parking lot, your radio goes into a fade. Okay, so how do you capture these kind of things? Okay, so you do it stochastically. But very important point is that for receive chain to do its job, the receive signal strength has to be adequately high. This is what comes from Shannon's Shannon's theory about communications, which is that I must have an adequate signal to noise ratio to be able to do successful decoding and get at the rate I'm transmitting, being able to get the bits correctly. For our purposes, we had also looked at different kind of wireless topologies. The most common one being where your wireless node talks to some sort of an access point. This is how Wi-Fi works. Sometimes access points are connected themselves using wireless point-to-point wireless links, but usually they are just on a Ethernet. And the other extreme is this so-called ad hoc networks, where every node is not only a source of sync, but it's also a router. And now to go from one node to another, you have to find your way through this thing. And more generally, and very typical of network embedded systems, we have kind of hybrids, where I may have nodes which may be next to a base station, next to an access point, and then other nodes which are kind of farther away. And then in which case they have to multi-hop. So many of the standards which are commonly used, ZigBee and Z-Wave, kind of follow this. Bluetooth, on the other hand, at least thus far, has been like this, the left one. But with Bluetooth 5, it is migrating to this hybrid model. So I think they are all converging towards this kind of a hybrid model. We spent some time talking about medium access control because that's very important to sharing the wireless link. And there are many ways you can share the wireless link. One way you can share is be in different frequencies, right? Another is be far away, right? So that your radio transmissions don't interfere. There are also ways in which you can make your signal use some fancy coding so that your signals may be there in the same space at the same time, but through these coding techniques we can separate them out. But the most common one is we try to arbitrate in time, and that's what MAC protocols do. So they basically come up with some sort of a protocol so that multiple transmitters will share the same channel in time, and while avoiding or minimizing collision, by being energy efficient so that you don't result in unnecessary packets being lost, being fair. So one way of avoiding collision is to basically say professor gets to transmit, no one else does, right, or something like that. That obviously doesn't meet the fairness criteria. You also want good throughput, so you want to make sure that making use of the channel successfully. AT&T, for example, ultimately is in the business of making money. So a scheme where much of the spectrum is lying unutilized is not very good. So throughput and bandwidth utilization. And we had looked at a very common style of doing things, which 8.11 also uses, which is this idea that before you transmit, you wait for a little bit to see no one else is transmitting. So kind of being polite, because if someone is transmitting and you start transmitting, then quite likely the receiver will hear you as well and the packet will be lost. One of the challenges in radio is that when you transmit, then your own signal, because it's traversing a very tiny distance, your receiver will hear your own signal very loud, whereas the other guy's signal is coming very weak. So you will never be able to see whether there is a collision. In wired networks, you can see whether what you are transmitting and what you are receiving are the same or not. But in case of wireless, you will always see them to be the same because your own signal is so loud, you cannot hear the other party. So they go for this politeness protocol. Wait for a certain time and only then transmit. And then you, once a transmission, if you see something is being transmitted, wait until again you see the channel becoming free and remaining free for a threshold period of time. So that's one part which is done in 811 using this time gap called DIFS. And then it also allows for acknowledgements. So the receiver can acknowledge, except that the receiver has to be pretty quick in acknowledging, because if it's delayed, then the other parties will think that the channel is free. So in particular, the receiver has to respond within an interval called SIFS, so that the channel is not seen to be free. And so there is a timing constraint that, as you can see, comes in there. And then there is also this idea that instead of using these things for, there's still, with all of this, there's still a tiny probability that the packet can be lost, because two parties may start at the same time. So there's a notion that you first do a small packet exchange to kind of preserve the channel and then follow up with the main data packet. So there are all sorts of ideas which come in. So this is one approach, which is no coordination, no agreement on time, but we are going to sort it out at runtime. And then the other approach is we agree upon the time. So we divide the time into a frame, we designate the slots, someone announces this is the start of a new period, and then within that period, node A has a particular time to transmit, node B has a particular time to transmit. So you kind of orchestrate things in time at pre-assigned slots. So variety of ways MAC protocols get done. Okay, so with all of that, let's try some things. And this is by no means coverage of all the topics, but I just wanted to give you a sense of the style of questions. Okay. So first, let's look at the scheduling things. The kind of questions you might imagine are things like I give you a task set and I ask you, is it schedulable? So if you look at this first task set, in this case is T equal to D. How would you approach it? I'm not going to solve them here, but I just want to give you.
Go for the processor utilization thing and check if it's equal to the other, like the formula for the number of tasks.
Okay, so we
Less than or
can,
equal to n.
or you can apply the other one, the geometric one, directly, because that's a better test. So U1 is C1 over, so it's 1 over 3, this is 1 over 4, and this is 1 over 3. Okay, so now product of, what was it, 1 plus Ci to or 2i, right? So it becomes, yeah, so 4 over 3 times 5 over 4 times 4 over 3 should be less than or equal to 2. Okay, and so 4 cancel, I mean you can work it out now. Okay, it's 20 over 6, which is, sorry, 20 over 9, which is 2 point something, so it fails. Okay, so anyway, you can fails this test. So what does it mean? It means it may be schedulable, so I have to go for the full test. Now you could see that the first two tasks are schedulable. If I were to just focus on this, then that is 5 over 3, which is less than or equal to 2. So I know first two tasks are by themselves schedulable, and the first two tasks in the rate monotonic case are the higher priority tasks. So I can actually just do the test for the final task. And to do the test for the final task, you compute the response time and kind of work of that. This Sorry, yeah, this should be 3. Sorry. Yeah. Okay. This one is similar, except that now it has these. So instead of using rate monotonic, we'll use deadline monotonic in case task 2 is higher priority than task 1 than task 3.
Instead of doing the response time analysis, there's this critical instant analysis that we can do, right?
It is the same thing, right? The response time analysis was this algebraic way of doing the critical instant analysis. You could either draw the diagram of the critical instant, or you can use that equation.
Because in the case of critical instant, you would just be doing it for all the tasks.
Well, you have to do it for all the tasks. It's exactly equivalent. I mean, the algebraic equation is doing exactly the same. Okay. You can now think of variants of this thing. I can give you this, and I can say C3 is unknown. Tell me how large X can be so that we still remain scalable. Okay, so this could be a type of question you can imagine. Again, simple algebra, you can work it out. Another one I can ask is the following: is this schedulable? If it is schedulable, tell me how much can I slow the processor by? Right? So I can, if it is schedulable, then one possibility is just schedulable, and I slow the processor even a teeny bit, I'll lose it. Another is there is some gap, how much gap it is. The reason that matters is because I can lower the frequency, I can do dBFS on that. The flip side, if it is not schedulable, then I have to crank up the frequency. What should that frequency be? So it's basically looking at the same set of equations, but from kind of different angles. Okay, again, some algebra. If you guys want to bring your calculators, be my guest, but usually the arithmetic is simple enough, but you might want to.
Here, in terms of the CPU frequency, we have only the utilization aspect, right? Like,
well, okay, so when you change the CPU frequency, what changes? The C, only C changes, right? That's the execution time. So if I lower the CPU frequency by a factor of 2, then each C will go up by a factor of 2. No, factor of 2, right? Power will change depend as V square F. So now we have to tell you how V and F are related, but let's say if the problem tells you, then you can again work it out. Okay. So unfortunately, questions like minimizing power I can't ask because they are computationally a little bit more intensive, but there are versions of those that also. Okay, you should be able to answer this thing about what if it is dynamic priority. So with dynamic priority, check for EDF. Now in dynamic priority, I only covered the case of t equal to d, so that's the only thing I can ask you. But if numerically at least, if it was d not equal to t, then you have to do a simulation, and you should be able to do that. You should be able to play out the EDF. Okay. Then you can expect questions which examine your knowledge on various kind of things. So like for example, this says reentrant function. Reentrant functions are those. Yeah, go ahead.
Question on the previous problem.
Yeah.
What in this is showing that it's dynamic apart from you telling us?
Nothing else.
Okay.
Nothing else. It's basically, I can take literally the same set of tasks and run it on a system which is dynamic or not, and that's operating system. So firstly, what you would say in something like this is, I'm going to use an EDF policy. So that immediately says that the operating system will have to follow the EDF policy. It has to keep track of it. And then you kind of show that it is schedulable. Okay.
Even for EDF, we run the same set of tests? Or?
Yeah. It's the same critical instant analysis. Yeah.
Okay, so we first check U, and if U falls,
No. U test and all are only for rate monotonic. Very important point. The U test is only for rate. It's not even for deadline monotonic. Okay, it is only for rate monotonic. It only applies for t equal to d case. Okay. So for example, going back out here, if I were to, for whatever reason, or maybe the question asks you, I tell you that give a different priority. Let's say I tell you that task 1 has the lowest priority and task 2 has the highest priority, then you cannot apply the U test. You only can apply the critical extent analysis or the response time test. Okay. So again, the test based upon U or U sub I are only for rate monotonic, which basically means only for the case Ti equal to Di with a rate monotonic priority assignment. Everything else, you have to do the simulation. Okay. Yeah.
One more time.
Yeah. Go ahead.
The previous slide also, you said that
Which was this?
dynamic priority preemptive schedule, but isn't EDF non-preemptive?
No, EDF comes in both varieties, preemptive and non-preemptive. Yeah. And I mean, you should be able to draw the waveform whichever way, preemptive and non-preemptive. So the difference in case of non-preemptive, you have to let the current task finish before you make the decision. Okay. So then you can expect questions which basically examine various concepts, and I'm just giving you some exemplar, but I basically going to assume that you're comfortable with all the concepts we have seen with respect to software concurrency and stuff like that. So this one basically says a reentrant function. So we had covered them orally in the class, but not formally in the slides. But reentrant functions are those which can be called in a nested manner. That is, I have a function running, and then maybe because of interrupt handler, or maybe I switch to a different thread, the same function is being called again. Okay. So that for a function to be reentrant, it has to follow some style. Okay. So it's basically asking, let's imagine some function bodies where this is the function body of a function, or this body of a function. Which one of these are reentrant or not reentrant? So what do you think? First one, reentrant. Okay, firstly, everyone knows what static does to a variable? What does it do? Static to a variable inside a function.
Sure.
No, not local to the function. You can see the opposite of that. Everyone can see it. Okay. So it's a shared. It's like a global variable that just happens to be in terms of scope of the name inside the function. Okay. But it is actually sitting globally. So every call to this function, when it refers to xxx, is referring to the same xxx. Okay. Whereas on the other hand, if static wasn't there, then xxx would have been on the where would it have been put? Stack, right? It's a local variable in that case. It gets put on the stack. So obviously, if it gets put on the stack, then only that call of the function is seeing it, right? Whereas static means don't put it on the stack, put it out on the global function. Okay. So we know now xxx and pointer 1, they're sitting in the global memory. The question is, so being static is a potential cause for trouble, but not necessarily always trouble. So it's basically saying, do you think there's any problem out here? In case 1. Yes, no, binary answer. So you're saying yes. So why?
Because xxx will be seen outside of the function, so if something else changes it, then
No, but nothing is saying that. Don't use this, right? So this is read only, so it's safe. Right? So in this
but
case,
when it's assigned to 5 and we see that y equals xxx times 0.
but every place it would be the same thing, right? Every call to the function is seeing the same static in xxx equal to 5. It's this function, right? So you could clarify. Okay, so I guess implied out here is that nothing else is using this xxx, right? So
Then why does it call it static?
Huh?
Then why is it static?
Stupidity. This one, pointer 1, both parties are going to do init list, and they might do it differently, and so they're going to trash each other. Okay, so this one is risky usage. So you should be able to reason about code like this.
Why is that one risky?
Why? What?
Why is it? Because
Wouldn't you call null?
because huh?
Like,
Because if I call this thing and then the interrupt handler calls this again, it will track pointer one with its own list. Or if another thread calls it, right? So by the time I return, so let's say I get pointer one equal to init list, and then later on I'm using pointer one, I have a different value.
oh, okay, so it's a handler called itself.
Yeah.
Uh,
So recursive cases or handler calling it. Let's look at this one. So I have a processor which has two states, on state, off state. In on state, it consumes P on power. In off state, it contains P off power. When it moves from on state to off state, it takes time P on off and consumes power P on off. And when it moves from off state to on state, it takes time P off on and consumes power P off on. My question is, what is the minimum idle time that would make it worthwhile to shut down the MCU? So let's say the software was running, and now it entered an idle state. How long would the idle have to be for it to be worthwhile causing the processor to shut down?
Larger than the sum of T on off and T off on.
Yeah, so you're kind of on the right track. So you basically have to compare against what if I had stayed put versus what if I transitioned, right? And then sort of work things out with that. So it's going to some algebra. One of the ways to approach this thing is you can say, I'm going to figure out what's the total transition time and what's the transition power. So transition power is a weighted sum, and transition time is T on off plus T off on. And then in terms of those, now you can reason. And now you can think of other type of questions out here, like what should my policy be? Let's say I were to tell you that my policy is wait for a threshold time and then shut down. What threshold will you pick? So think about those kind of questions. And by the way, part of the answer will also depend upon whether P on off, P off on are smaller than P on or bigger than P on, right? So this results to, for processors, so it's kind of an interesting thing. You might say that why would this transition power will ever be larger than P on? Can you think of systems where cost for transitioning to on-off state may actually be the power may take more power during that time than when it is just running?
Higher bit processors.
No, but why would higher bit processors take more time during transition? And doesn't have to be processor. Can you think of systems where when they are transitioning from on-off or on-off, on to off or off to on, they consume more power than when they were simply on?
Some huge server.
Huh?
A huge server.
Why would they?
Because most of the time it's on, it's idle. And when it turns
No,
on,
I didn't mean in that term. So let's say, because we can think of this as, so I'm not thinking in terms of this thing itself having any states. Okay, so this is just on, it's running. Okay, so versus kind of moving into a low power state or some form. So so can you think servers and computers can when they are shut down and when they're activated, they can actually take more power during transition. So can some other devices. So I'm just looking for some examples of these. Because as you might imagine, if P on off and P off on are very high, then it's a troubling thing, right? Because that means if I cycle through this, it may actually consume more power than if I had the state put out here. My idle time would have to be really much longer because of that. So, yeah, couple of things. So firstly, disk drives. Okay, disk drives they spin up mechanically. So when they start from static thing, and when they spin up, they have to fight against what? What kind of friction? Static friction. Okay, static friction is higher than the dynamic friction, right? So actually, if you look at the current profile for a disk, peaks and then settles. Something similar happens with processors also. When you're starting out, the capacitors are not charged up. So when you start up, there's a rush of the current to charge up the capacitors, and then it settles down. So many systems have this thing where, depending upon what kind of state you're looking at, this thing actually can be higher than P on. But in any case, your policy and your break-even point will partly also depend upon what's the average transition power. Um, so anyway, so you should be able to think about this system and see if you can kind of reason through this. And likewise, while I don't have any problem listed out here, I should be, you should also be able to do this kind of analysis for like big dot little type systems also, similar concepts.
So for this question, would the idle time also include, like, when you're calculating, also include TI?
Okay, so let me, so idle time means that the idle time from an application perspective. So your application just transition into idle. And then like maybe it finished processing the sensor sample, and now the next sensor sample is T idle away. And you have to decide whether to shut down.
So when calculating the energy consumed for T off, you should subtract.
Well, okay, so if I had stayed put in T on, then I would consume T idle times P on. If I were to transition, then I have two possibilities. One is T on off plus T off on is greater than T idle, in which case I should not do it because it will elongate my time, it will delay things. So if it is smaller, then for part of that T idle, I'm paying this energy, and then for T idle minus T on off minus T off on, that time I will be doing T off, and you're going to sum those things up.
But if it's T idle, the power that's still consuming is T on.
If I stay here, right? So I have two choices. One is stay put, and the other is do this game, right? And break even says what is the value of T idle at which the two options are the same, because any T idle longer than that, I'm better off going through this, right? Anything shorter than that, I should just stay put in the one state. And then power management boils down to making some prediction about, because remember, there are two situations. One is I know when the next interrupt is going to come, and the other is I have no idea, so I have to predict, right? And you do predict. You can have various kind of heuristics to do that with some trade-offs. Okay. Sometimes you do know when the next thing is going to come. Like for example, take our favorite periodic task setting, right? If the thread has told me it comes every second, and I know when it last came, then I know when it will come next, right? And I can make use of that. So depends on kind of setting. On the other hand, if it's an interrupt coming, kind of a network packet arriving, a lot of jitter, I don't necessarily know that. So what I am expecting for these kind of things is that you should be able to apply these concepts to kind of these kind of settings. Okay, just do some simple algebra to be able to answer these kind of questions. Okay. Then I have you can expect these kind of questions, which basically are kind of just checking lecture knowledge primarily, or very straightforward application of it. So what ways an ISR differs from a normal function? We actually talked about it earlier. Again, what ways does it differ? Huh? Preserve all the registers and restore them, and it should not do anything which takes super long time. Okay, two things. What are the pros and cons of using ADC versus PWM? We talked about that also. Resolution versus tempo. Okay. What are pros and cons of events versus threads?
Stack size.
Stack is one, right? And programming, one gives you kind of a linear abstraction of the thing, another one you have to mentally reason about where you are in the code. Then things like, what's the resolution of an ADC with 12 bits and a reference volt of 3 volts? Super simple. 3 divided by 2 over 12, right? Okay. So you are employed to make a sensor system. You have choices of Bluetooth, Zigbee, or Wi-Fi. And you are going to be communicating accelerometer data at 100 Hertz, where each sample is 8 bits. Which radio would you pick and why? And then later on, we have a version where we say it's image data. Which radio will pick and why? So this is just your qualitative understanding of these. Okay, which one would you pick?
say more about the second question, the pros and cons of these
ADC versus PWM? Sure, yeah. Remember, the challenge with PWM is that we have a time frame that we have to pick. Okay. Now, let's say I have an ADC. Let's say I want to be able to change the output signal every time t. That means my frame size has to be time t, and within that I have to do the whole counting. So if I have n bits and I am updating at a rate of t, then that means I have to count 2 to the power n in a time period of t. Now let's say I'm generating something which is like 1 mega sample. I can do that with DAC very easily, whereas with something like this, I would have 1 mega sample, 1 megahertz multiplied by n to the power n, which in this case could be, I don't know, let's say if it's 32, then suddenly you're talking about a gigahertz counter that can be problematic. So by translating resolution into temporal resolution, we can reach to very high clock frequencies, which may be power hungry and also problematic to that.
So that's for PWM.
That's the con of PWM. The pro of PWM, anyone? It's all digital, right? You can implement it just using stuff. I don't need any fancy analog circuitry.
What is the purpose of the counter in PWM?
So that you can decide when to transition, how long to keep it high versus low. So you will have a counter with a comparator,
Oh, okay.
right? Yeah, you have to decide when to.
Yeah.
So that's why you need the counter. You're counting time. Okay, that's that. Okay, so here is basically just seeing, are you aware of like the thing to keep in mind. So Wi-Fi goes, normal Wi-Fi started at a few megabits per second, and now it goes up to gigabit per second type thing. Zigbee is around 250 kilobit per second, and Bluetooth is 1 to 2 megabit per second, right? So it kind of gives you a sense of where there is light. And then there are other issues between the range and power consumption and things like that. Actually, very much the same considerations which we had with processors, which is complicated processors or higher performance processors are good at bulk stuff, but they are bad at duty cycling. So if I have to send small amount of data, a problem with Wi-Fi is that the overheads sort of begin to kill you, and if you're sending things at a relatively low rate, then shutting things on and off with Wi-Fi can be very problematic. It can take a lot of time. In fact, when a Wi-Fi radio comes back up, for it to just sync back up with the base station can take a lot of time. So for infrequent or low duty cycle type small tasks, you're better off with Zigbee or Bluetooth. Now, even with Bluetooth, we talked about that how classic Bluetooth can again require seconds to sync up. Okay, so usually Zigbee is really well optimized for. But by the time you start hitting images, you basically will need to max out Bluetooth and Zigbee. You'll either go Bluetooth or quite possibly Wi-Fi. So I want you to have a sense of like where do these different technologies. This one is a simple one. So I have a UART which is 19,200 baud rate, no parity, 8 data bits, and 1 stop bit. So what is the throughput of this?
200.
Huh?
19,200.
Nope. You're forgetting something.
Oh, yeah.
No. There's a start bit too. Right, that's 10. The start bit is always there, right? Okay. And likewise. Okay, so basically you kind of, hopefully you're getting the hang of just these kind of conceptual questions. And yeah, so that's all I had. Any questions from you guys?
Can you say more about how to calculate the throughput of this?
This one? Yeah. So there are actually, in this case, there are 10 bits which are going out every time. Okay, and 8 out of 10. So it's 8 out of 10 times 19,200. So it would be. hope my arithmetic is right. 15360. Okay. And likewise for I2C or SPI.
So we don't need to count the stop bit. That
We did 8 plus 1 plus a start bit. So 8 plus 1 plus 1, which is the start bit.
We worry only about the rate of this data bits, not the entire set.
Yeah. The throughput means the good put, right? The good bits, the bits that matter to you, right? So every 10 bits that I'm sending, only 8 of them are real payload. This is important, this notion of throughput, because when you
So the denominator is 10 because we have 8 data bits.
8 data bit, 1 stop bit, and 1 start bit.
1 stop bit.
Okay, and out of those, 8 are my data bits.
Yeah, the 8 of data bits that matters.
That matters, yeah. Generally speaking, so the challenge that you get from this is the following. Every time you communicate using some packet, there's always an overhead with it. Header, error checking, stuff like that. So for you to get throughput high, what would you do?
Make header small.
Okay, but I could make header small, but usually that's not much of a choice that we get. So if I cannot make header small, what can I do? Make payload big, right? Now to make the payload big, I have to collect data, which means latency goes up, right? Because I have to wait longer time to collect that data. That's one problem. The other problem is that if packet size goes up, what goes up? So let's say my bit error rate was 1%. 1 out of 100 bits get trashed. So now what is my packet error rate? If I have n bits, then my packet error rate is n times, right? Okay. Or I can work out, sorry, not n times, 1 over 100 times to the power n, right? Okay. So for the same bit error rate, the packet error rate, actually I messed it up, okay. So, yeah, so it would be 1 minus 99 over 100 to the power n, okay. So let me, nope, it's not the same, okay, add a page, okay. So let's say my bit error rate is 1 over 100. That is, with probability 1 over 100, the bit goes bad. So what is my packet error rate? So that is 1 minus all the bits going successfully. So it's 1 minus 99 over 100 to the power n, right? Okay. Now if n goes up, packet error rate. Okay. So long packets are bad from this perspective because packets are the unit of retransmission. If a packet goes bad, I have to retransmit the whole thing. Okay. So going back to this issue, small packets are bad because overhead is high as a percentage of the payload, throughput goes down. On the other hand, big packets are bad because the chances of the packet going through goes down. Okay. And so it's the balance that you have to somehow strike. Okay, and besides the delay part also, right, which is long packets. So now, in case of UART, it doesn't matter, but in case of radios, that is an issue also. Okay, the other thing is, so what are the kind of overheads we talk about in, let's say, a radio? So if you look at a whole packet, so first thing is, I'll have a wake up thing. I have to turn on the transmitter and stuff like that, right? Then usually there is a preamble. This is like the start bit. Now in case of radios, what this preamble does is it tells the receiver, I'm here, this is my clock frequency, stuff like that. It basically, you send a test tone there. so that the other side can learn your clock frequency, and also there's going to be a preamble. And then there is a header. This header would have address, for example. It will tell which receiver is it meant for. And then finally you'll have payload. And then also at the end you will have some error checking. So if you look at a lot of these standards, what happens is that to send a payload, you may have 30, 40 bytes worth of this overhead. So you're sending a byte or two of sensor reading, but you're sending maybe 30, 40 bytes of additional jump. Okay, so your throughput can actually be pretty low if you are sending very small amounts of data. But if you are sending lots of payload, then the challenge is the one which we face up there, which is long packets. You are making it unlikely they will go through successfully. The reason long packets don't go through successfully, besides this, is also the two sides during the preamble learn each other's clock, but the clocks are not perfect. So as the packet is longer, the clocks drift apart, and pretty soon at the end, they're sampling the wrong bit. So that's why there is a limitation on how long your packet can be, or how many bits you can send in one go. So all of those things come into play together, which basically kind of create this tension that efficiency requires that you should have large payloads so that you can have good throughput, but the physics of the circuits or physics of the system force you towards smaller packets so that you can successfully transmit them. And the balance between the two is what we are going to go for. Which is why, like for example, you would see like Ethernet used to have packet sizes of a few thousand bytes, 1,536 bytes or 8,000. Okay, but with the new gigabit Ethernet and all, the numbers have gone up to 16,000 or 64,000 jumbo packets and all. And the reason is that as circuits and all have improved, they're able to sustain better BER over longer packets now. And also the header overheads have gone up with some of these technologies, so they're forced to go towards longer packets to gain efficiency. On the other hand, short-range radios, like when you're sending heart rate or these kind of things, your heart rate is probably a few bytes. You want it to be very efficient somehow, right? And unfortunately, efficiency takes a big hit. So like Bluetooth LE, which is what we are using, its native baud rate is 1 megabit per second. So in theory, peak you can send that. In reality, you send it maybe 30, 40 kilobit per second. Okay, rest goes into all the overhead. So that's a big challenge in getting good support. So that one was just forcing you to think about like what's happening in just the UARTs. I mean, even there, we don't even have any parity bit. If you have parity bit and all, I mean, they go down further. So a term which is often used is good put, good throughput. Okay. Any other questions?
Could you elaborate a little bit more on the previous question you had about the CPU utilization? Like, by what factor can you slow it down?
Sure. So what this is saying is that let's say you find that this is schedulable. Okay. Then how much can I slow this thing down so that it remains schedulable? So let's say I can slow it down by a factor alpha. Okay. Slow down by factor alpha means that all the delays are going up by factor alpha. So which means all my C's will become 2 alpha, 2 alpha, 4 alpha. And now you have to find the value of alpha for which it remains schedulable. And at that stage, it's a bit of an algebra problem. One is obviously you can approach it purely computationally, not in an exam setting, but just do a hunt on alpha and kind of find it. But just by writing down the expressions, you will see what you achieve. And the other one I had was kind of a similar thing where I said, what can X be Whatever I've covered until last Thursday, there was no lecture on Friday. Yeah, it's there, but we were still in the midst of Bluetooth, so I'm not going to ask you anything deep about Bluetooth. Tomorrow's lecture will be on Bluetooth then, but that's not an exam. Any other question?
So for the question that which function is reentrant, so you said the second one will cause some problem, right?
Yeah, because it's writing. Anytime you write to a variable, then you have a problem that, where is it? Yeah, then you have a problem that two parties both are writing to it, they're trashing each other.
So how about the first function A?
First person A, since we are only writing a constant 5, so even though both parties are writing to it, they're writing the same thing. So it doesn't matter. Whereas in another case, they're initializing some sort of a list in, so they're storing a pointer there.
Because it's just a constant, so.
Yeah, so in first case, it's just a constant, which is why he was saying the point, why did I write it that way? Because kind of stupidly written. You should probably say const static or something. Firstly, there's no reason for it to be static. You should probably just say const int xxx equal to 5. Okay.
Even if it weren't const, if you're still assigning the same 5,
yeah. So what I would suggest in terms of preparation for something like this, so firstly, again, the material in the course is not conducive to any sort of deep theoretical analysis, and also that those kind of, or even for that matter, deep numerical analysis. If those things are out, you should go through the lecture notes, make notes about the important points, and I think more about, so that you're not caught by surprise when, oh, what does it mean, kind of thing. Okay. I think for the scheduling part, you should perhaps make notes of those key. There are 2 or 3 formulas. The power part, there is probably only one formula, or a few, right? I mean, power is proportional to v square f, and speed is proportional to frequency, and I mean, that's kind of obvious. Yeah, okay. And then I expect that you would know things like that all electromagnetic waves do 1 over d square in free space, those kind of high school physics stuff. You should know. Okay. Questions? Any more?
Are you going to put up answers for any of these? Just because we've never had any homework or anything dealing with this before.
I can put up the answer, sure. But you really need it?
Just as a check, right?
Okay.
If we have some understanding that's wrong.
Sure.
Is this PowerPoint already available online?
No, I was working on it until just before the class. I haven't put it yet. I will do it. But feel free to just exchange notes on this on Piazza among yourself. I mean, okay. So again, cheat sheet 1, 2-sided, 8.5 by 11, and if you want to bring calculator, that's fine. If you don't have a calculator, you want to use a calculator on your phone, that's also fine with me, but please don't use it for anything else. I realize that you may not have a calculator, so but you shouldn't need it. I mean, the numerical part you should be able to do by hand. Okay.